Okay, so the first question that the professor has given us to solve is this, that the value of the gamma function at n plus 1 should be equals to n factorial. So let's prove this. Okay, the gamma function at n is as follows. The integral from 0 till infinity of e minus x n minus 1 dx. So the value of the gamma function at n is equals to 1 is going to be from x 0 till infinity e minus x, and x power 0 is just a 1, so we don't need to write that. So then we take the derivative integral of this, and the limit goes from 0 till an infinity. Okay, we know that the function e minus x looks like this. So it converges to a 0 as x approaches infinity. Therefore, I have a minus 0 plus e power 0, which is a 1. So we have a 1. Okay. So moving on, what is the value of the gamma function at n plus 1? I'm just going to put it in the integral over here, but I'm going to replace n with a n plus 1. So n plus 1 minus 1 is just going to give me a power n. So e minus x power n dx. And now I'm going to use integration by parts. So I'm going to use integration by parts. Okay, so I'm integrating this. So the integral is minus e minus x, and I'm going to keep n x power n as it is. The limit goes from 0 till infinity. Then a minus integral from 0 to infinity. Again, the integral of e minus x into the differential of xn. Okay, so we have this expression, and then we have a plus, and then we have a n over here, and we have the integral from x0 to infinity e minus x and x n minus 1 dx. First, let's evaluate this limit right here. I note that the limit of e minus x and xn as x approaches infinity, it doesn't make sense for us to multiply a 0 with an infinity, right? So we can write it like this: the limit of x power n over ex as x approaches infinity. And now we have an infinity over an infinity, which is also, it's undefined, because we have the numerator and denominator both tend towards an infinity. Therefore, we can use the L'Hopital rule, which is that this limit is the same as the limit of the derivative of the numerator and the derivative of the denominator. So the derivative of the numerator is nx n minus 1 over ex. Again, we have a situation where the numerator and denominator are both tending towards infinity once again. So we're going to keep doing this until we get x to the power 0, which is basically equals to a 1. So just continuing to do so, I'm going to be left with the n factorial and then the limit of 1 over e power x as x approaches infinity. Now the limit becomes an n factorial. I want to make it as compact as possible. Okay, so we have a n factorial multiplied by 0 because 1 over infinity tends towards a 0, so we have a 0 here. And next I need to find the limit of e minus x power n as x approaches a 0, which is e power 0 into 0 power n, which is simply a 1 into a 0, therefore a 0. So basically when we see the limiting behavior of this expression from 0 till infinity, it's just a 0 plus a 0, which is a 0. So this expression right here collapses to just a 0. So we have, what do we have left? We have a gamma at n plus 1 is equals to n and this. But this is also the value of gamma at n. Okay, so if I keep repeating the process, like if I write a gamma at n plus 1 is equals to n gamma n, and then I use the same equation to fill in the value of gamma n, which is going to be n minus 1 into gamma n minus 1. So this is going to be n into n minus 1 into gamma n minus 1. So if I keep repeating this process, I'm going to get like an expression like this, an n minus 2, and then an n minus 3, and so on till I have a 1, and then the last expression would be from x0 till infinity with e minus x, and that would be an n minus an n, right? Because we are going down from n to n minus 1, n minus 2, so on, till n minus an n. So this is the last expression that we will have. And this whole thing right here is simply n factorial. So I write a n factorial here. And this expression, the remaining from x0 to infinity, e minus x dx, the integral of this is simply a 1. So, or maybe I should show this. We integrate it, we put the limit from 0 to infinity, and we have an n factorial multiplied by a minus 0 plus a 1. So in the end, we're just left with multiplication with a positive 1. So therefore, the answer is n factorial. Okay, so I hope I've made this clear. So the gamma function at n plus 1 is equals to n factorial. What this means is that if they ask you the value of gamma at n is equals at 5, it's just 4 into gamma at 4, and then that is just a 3 into the gamma function at 3, and that's equals to gamma 3 is 2 into the gamma function at 2, and then that is 1 into the gamma function at 1. So we have a 4 factorial into the gamma function at 1, which is basically 4 factorial into a 1. So it's just a 4, actually, so sorry, this is a 5 factorial. Is it a 5? Oh, no, it's a 4 factorial. Yeah, it's a 4 factorial. Okay. What if we have a fraction? I'm going to prove this later, that the gamma at a half is equals to under root of pi. I will prove this in a bit. Prove this later. Okay, in the same video. Okay, so suppose the question is gamma at 7 by 2. So a 7 by 2 minus a 1 is a 5 by 2. So this is going to be a 5 by 2 gamma at 5 by 2. A 5 by 2 minus a 1 is a 3 by 2. So I'm going to get a 3 by 2 gamma at 3 by 2. A 3 by 2 minus a 1 is a half. So I get a half multiplied by gamma at 1 by 2. Sorry, this needs to look like this. And therefore, I have a 15 over 8 into the under root of pi. I hope that's easy to understand. Okay, moving on. The next question that the professor gave us is that he wanted us to know how to convert the gamma function into a gamma distribution. I'm not sure how many of you are familiar with statistics, but in order to have a valid density function, the integral on the whole range of that particular function from negative infinity to positive, whatever the limit of that particular function is, the integral has to be equals to 1. And if you want a valid mass function, so this is basic, the density function is continuous time and a mass function is discrete time. So in that case, the probabilities again have to add up to a 1. So probabilities have to add up to a 1. And again, whatever the minimum to the maximum range of that function is. Since the gamma function is and distribution is a continuous distribution, so we are basically concerned with finding a function which fulfills this requirement. Okay, so moving on with our solution, we know that the gamma function at n is equals to the integral from 0 to infinity of x n minus 1 e minus x dx, right? And suppose that the gamma distribution, this is the distribution, let's call it the density function of gamma distribution, which I need to find, right? So if I am searching for this, what it needs to satisfy is that from 0 to infinity, the integral has to be equals to a 1. So I need to find a gx which satisfies this. That's the only way it's going to be a valid density function. Okay, we know that the integral, the gamma function at n, which we defined as 0 till infinity of x n minus 1 e minus x dx, the value of this is a n minus 1 factorial, right? And this is actually not equals to a 1. So therefore this itself cannot be our gamma function, because over the whole range the integral is not equals to a 1. So what kind of manipulation can I do to ensure that the integral becomes 1? So if I divide this whole thing by n minus 1 factorial, I'll get this expression, right? Wait. Divided by n minus 1 factorial, and therefore I have a 1 on this side, because n minus 1 factorial divided by n minus 1 factorial is a 1. And since the limit of this is on the values of x, not on the values of 1, so this is just a constant which can go inside. So this can go inside from 0 to infinity, x n minus 1 e minus x over n minus 1 factorial dx, and the answer is going to be a 1. So what is the gamma function? Look at this right here. The integral of this expression from 0 to infinity is a 1. Therefore the gamma function is x n minus 1 e minus x over n minus 1 factorial. So there you have it. That's the gamma function, and it's a valid density function. Okay, the next question this professor gave was that he wants us to show, this is going to be question number 3, that the integral from 0 to infinity of e minus ax x n minus 1 dx is the gamma function at n over a power n. So this is what we had to show. Okay, let's use the substitution of y is equals to ax. Therefore dy over an a will be equals to dx, and whenever x is equals to 0, y is equals to 0. Whenever x is equals to infinity, y is equals to infinity. So we have the following integral. We have a y0 to infinity e minus y, and over here x, what is x? So x is y over n a. So x n minus 1 is simply y n minus 1 over n a n minus 1. Okay, so I write this y n minus 1 over n a n minus 1, and we have to replace the dx with the dy, so I have a dy over n a. Okay, so this simplifies to 0 till infinity e minus y y n minus 1 over n a n dy. Since the integral is actually just on y, then a power n is actually just a constant which we can take outside the integral. So that's just a constant, I take it outside. And now we have 1 over a n, and this expression is actually the gamma function at n, and because y is just a dummy variable. So therefore that's thus the gamma function at n, and therefore we have our proof. And one more question before I end the class is the last question, quiz 4 I believe it's called, is that we had to prove that the gamma at power half is equals to under root of pi. So gamma at half is simply 0 till infinity e minus x. X would be a half minus 1 is a minus half dx. Okay, so if I use the substitution x is equals to y square, I'll get a dx is equals to 2y dy. Okay, and x minus a half would be y half 2 multiplied by minus half is just a minus 1. Okay, so if I use this substitution, our integrand, and whenever x is equals to 0, y is equals to 0. Whenever x is equals to infinity, y is equals to infinity. So y still goes from a 0 till infinity. We have a e minus y square into a y minus 1 into a 2y dy. Therefore, my expression, the y's cancel out, right? And we get the 2 can go out, y goes from 0 to infinity, and we have a e minus y square dy. Okay, if I take the square of both sides, what will I get? I'll get the 2 becomes a 4, so I get a 4 here, and this whole square. Remember in the previous lesson which I took on campus, we can convert this into a double integral by writing this as, because x and y are basically just dummy variables, so I can remove the square and replace x y with an x everywhere, and this way this becomes actually a double integral. Okay, so what do we have? We have a 4 double integral from x 0 to infinity, from y 0 to infinity, e minus x square plus y square dx dy. And if you will remember, we did this we did a transformation from xy to polar coordinates, which was r theta, where y is equals to y is opposite, right? So that would be sine of, yeah, so r sine theta, and x was r cos theta, and we had x square plus y square is equals to an r square, and we took the Jacobian, and the absolute value was actually an r. So we've done this in the previous lesson. So when I do this conversion, I get the following answer. So the 4 is just a constant that remains there, and now the integral becomes this actually. Theta goes from a 0 to pi by 2, 90 degrees, because we have a quarter disk. So that's like a, this is the disk, right? That's just a circle. When x is greater than 0, y is greater than 0, the angle lies between 0 and 90 degrees. And the radius can go from 0 to infinity. Okay, we have a e minus r square r dr d theta. So solving this, I can write the double integral like this. Theta goes from 0 to pi by 2 d theta. We don't have a theta here, so I'm just going to put a 1 there. And we have r that goes from 0 to infinity of e minus r square r dr. Since the derivative of this is present here, therefore I can just simply I don't need to use substitution. I'm just going to do it directly. Okay, so the theta, let me just put a bracket. Theta goes from 0 to pi by 2, and we have a e minus r square r over a minus 2r, and this expression goes from 0 to infinity. Okay, so we get a 4 pi by 2 minus a 0. The r and r cancel out here. E minus infinity over a minus 2 plus e power 0 over a 2. Okay, so we have a 4 pi by 2 into this is a 0 plus a half, so a half. So we have a 4 pi over a 4, which beautifully comes to a pi. Okay, so therefore we have the square of this being equals to a pi. Therefore the gamma function at half is just the under root of a pi, which is what was required. Anyhow, so these are the first questions the professor gave. I'll scroll this up and show you what we've covered so far from the document that the professor shared. Okay, so we've done quiz 1, and I've covered this in this video, so this is done. And we've done this, yeah, we've done this as well, and we've also done this part. So we're done with the first 4 quizzes. In the next class we can continue. Actually, I've done this as well, we've done this as well. So we'll continue the next class with quiz 5. Take care for now. Allah Hafiz.